Hi, my name is Nilesh Mehta. So I'm going to present the work we are doing on energy efficient schemes for wireless sensor networks. And this work focuses especially on an important aspect, which is correlation between measurements made by different sensor nodes. So this is joint work with Sayan Sen Gupta. We are both in the EC department at the Indian Institute of Science in Bangalore. So let me just set up the context for the problem. So we're going to be looking at a fundamental problem in detection. That's the binary hypothesis testing problem. This has many applications, such as target detection. Is there a target present or not? Spectrum sensing, which means is there a primary that is transmitting or not? So that if the primary is off, you can transmit as a secondary. Fingerprint detection, and so on. Basically, in this hypothesis testing problem, there are two hypotheses which we'll call H1 and H0. H1 is the scenario where, for example, the intruder is present or pollution is present in case you're doing environmental monitoring, or the spectrum or the primary is present in spectrum sensing. And in H0, all of these are absent. Now, since we're looking at wireless sensor networks, an important consideration in these networks is energy efficiency. It's important to have protocols that are as energy efficient as possible, because it's only improved energy efficiency that leads to an improved lifetime, and a long lifetime is very critical to make wireless sensor networks practicable. So what I'll do in the rest of the talk is give you a background on a scheme called the ordered transmission scheme, and why it's so interesting from an energy efficient point of view. And then we'll talk about our work on making the scheme correlation aware. We'll do a performance evaluation of the proposed scheme, and I'll then summarize. So let me set the problem context. So what we're looking at is a sensor network with uh, n sensors, y1 to n, and these are the measurements made by them, y1 to yn. So yi is the measurement of node I, and based on these measurements, the fusion node or the data aggregator has to make a decision about whether hypothesis H1 happened or hypothesis H0 happened. That's the problem. And turns out that the error optimal decision rule in this case is the following: that you should take the log likelihood ratios of all the n nodes, add them up, and compare them to a threshold beta. If it's more than this threshold, you declare H1 to be true. If it is below if it is less than beta, you declare H0 to be true. So this is also called the Bayesian testing framework. And this beta is a function of the cost you would incur if you made the right decision, the more increased cost you would incur if you made a wrong decision, and also the prior probabilities of H0 and H1. But it's a constant as far as we're concerned and can be computed. Just to recall, the log likelihood ratio definition is that it is the logarithm of the ratio of two conditional probabilities. In the numerator is the probability that you get a measurement yi given h1 hypothesis is true, and in the denominator is the conditional probability that you will see yi given hypothesis h0 is true. And this arises a lot in detection. Now, in a conventional scheme, when the sensor nodes are spatially separated from each other and from the fusion node, the way you would implement this error optimal decision rule, the one that minimizes the error probability, is that you would make every node transmit its LLR. So first it would compute it from its measurement, then transmit its LLR to the fusion node. The fusion node would accumulate all these LLRs, and once it receives all the n LLRs, it would compare it with beta and then make a decision. The problem with this scheme is that it requires n transmissions, where n is the number of sensor nodes. So this is where the ordered transmission scheme comes in and takes a very different view of the problem. Instead of making the nodes transmit in a sequential order, 1, 2, 3, 4, 5, so on, it makes the node transmit in an order that depends on their measurements. So here's the scheme. The nodes first take the log likelihood ratio and compute their absolute values. And the nodes transmit in the decreasing order of the absolute values of the log likelihood ratios. So the first node to transmit is the node with the largest absolute value of the log likelihood ratio, and I'll denote by square bracket 1 the index of that node. It's a very convenient order statistics notation. And then the next node to transmit would be the node with the second largest absolute value of the log likelihood ratio, and so on. And when the node transmits, it sends a packet, and in the packet it includes its log likelihood ratio. So the fusion node would get that node's LLR log likelihood ratio when the node transmits. And the important thing is that the fusion node can decide early. How, I'll tell you, but it does not have to wait for all the end transmissions to come. So instead of formally defining the scheme mathematically, I will illustrate it with an example. So the first node to transmit is the one with the largest absolute value of the log likelihood ratio, and when it transmits, it sends its log likelihood ratio. Now, what the fusion node does based on the measurement it has received is it compares with an upper threshold, uh, and if it's more than the upper threshold, it declares H1. It compares it with a lower threshold, and if this measurement is, or LLR is below this lower threshold, it declares H0. If it is in the gray zone, in the middle, it just waits for the next transmission. The important thing is that these thresholds are functions that are things that the fusion node can compute. So this is a function of beta, which we saw before, and the received measurement, which the fusion node has. And this is also beta minus that. So both of these can be computed. So if it waits, then one more transmission will happen, which is by the second best node. With the second largest absolute value of the log likelihood ratio, it will send its log likelihood ratio in the packet, and now the fusion node compares the log likelihood ratios it has received until now. And if it exceeds a threshold, it declares H1. If it exceeds another lower threshold, it declares H0, or it waits. And again, these thresholds are functions that the fusion node can compute based on the information it has till now. And interestingly, these thresholds shrink. So you can notice here, this upper threshold is lower than the previous round's upper threshold. This is larger than the previous round's upper threshold. And when one more measurement comes, for example, these thresholds will again move closer to each other. And this process continues till the fusion node makes a decision, at which point it terminates and no other node transmits. And in fact, you can show that if you receive, in the worst case, n measurements, both these thresholds become exactly equal to beta. So eventually, the scheme will make a decision. And the really important thing is, if it does make a decision, it's exactly the same decision that the fusion node would have made if it had all the n measurements available with it, all the n LLRs available with it. That's the really interesting part about the scheme. So, and this is really what makes the scheme exciting. In their paper, Blum and Sadler showed that it provably reduces the number of transmissions required on average by at least 50% without compromising on the error probability. So you achieve the same error probability as the optimal scheme in which all nodes transmit, but it requires far fewer transmissions. And this translates directly into energy efficiency, because fewer the number of transmissions, the more energy efficient the scheme is. And the reason why it does so well, let me give you the intuition for it. So basically the two things that the scheme is going for it. First is that when you order the nodes based on the absolute value of the log likelihood ratios, when you've received some measurements, you actually have information about the measurements you've not received also. So let me give an example. So say you've received the k best measurements. That means that the remaining measurements, the absolute values of the log likelihood ratios, are all less than the k best measurements that I've received. And therefore I know the range in which they can lie, and therefore I can bound the sum LLR to some extent. The other thing is, and this is a really smart thing that the scheme does, is it basically makes nodes that have more information to convey about the hypothesis transmit earlier. And what do we mean by more information? Well, the absolute value of the log likelihood ratio, in fact, is a good measure of how informative the node's measurement is. If the node is very sure H1 has happened, you can think of the log likelihood ratio being very large, very positive. And if it's sure that H0 has happened, then you can think of the log likelihood ratio being very negative. In both cases, the absolute value will be large. And it's when the node is not sure that this absolute value will be small. So what this scheme does is it makes the nodes who are very sure about the measurements, who can contribute the most to the decision, transmit early, and the nodes are not sure, transmit later. So these are the two things that really lead to the gains. And before I move further, let me clarify that this scheme can actually be implemented in a distributed manner. Recall that the scheme requires the node to transmit in the decreasing order of the absolute values of the LLRs. Now, upfront, no node knows any other node's LLR. So one can argue, hey, how does it know when to transmit? So here's a very simple way to do this. This is called the timer scheme. If you're very interested in the scheme, I request you to read this paper we had written in 2010, which discusses the optimal design of the timer scheme itself. Here I'm going to explain it using an example. So the way the timer scheme works is very simple. Each node sets a timer, and the timer is a function of what we call a metric. So in this problem, the metric is the absolute value of the log likelihood ratio, the basis on which we order the transmissions. And the node transmits when its timer expires. The key thing is that the way you set the timer is a decreasing function of its metric. So the larger the metric, the smaller the timer. For example, this is a 1 by x function. So the timer is inversely proportional to the metric. So you can see that the first node to transmit will in fact be the node with the smallest timer, that is the node with the largest metric or the largest absolute value of the log likelihood ratio. The second node to transmit will be the node with the second largest value, and so on. And so you can see here, no node needs to know any other node's absolute value of the log likelihood ratio, but the nodes end up transmitting in the decreasing order. So it can be done in a distributed manner. Okay, so now we look at the problem we're interested in this paper, which is that in many practical scenarios, the measurements can be correlated. What I mean by that, I'll bring out with an example. So here is one example of Gaussian statistics, where under H1, the received vector y1 to yn is a Gaussian random variable with mean 0 and a covariance matrix R. Now, if this covariance matrix R is not a diagonal matrix, then essentially you've got correlation between the measurements. Under H0, in this example, essentially what you're measuring is noise. So essentially you've got noise only measurements, nothing is happening, you're measuring noise. And in the design of the OTS scheme that I've discussed till now, it was assumed that the measurements are independent. And it is only when the measurements are independent conditioned on the hypothesis that the decision statistic becomes add up all the LLRs and compare them to the threshold beta. Otherwise, this doesn't happen. When you have correlation, for this example that I'm mentioning here, something else happens. So if you look at the decision statistic, and I'm going to skip several steps here, you can show that it's a quadratic function of y. So it turns out to be y transpose gy, where G is a matrix that depends on the covariance matrices under H1 under H0. So it's like I minus R inverse scaled. But it's basically something that can be computed. And if you open this up, you will get it to be a sum of quadratics, just like it was before, some summation involving each of the nodes measurements or LLRs, but also you get this cross terms arising, where this term depends on the product of the measurement by node I and the product of the measurement by node J. So this raises several questions about OTS. First is, you can see now that how useful a measurement is depends not just on its own value, the node's value, but it also depends on its product with other nodes measurements, which the node doesn't know. So the question arises, can I implement such an ordered transmission scheme in a distributed manner now? Secondly, what do I even transmit? On what basis do I order the nodes? Clearly, it's not going to be the LLR, it's got to be something else. And this is the problem that we solve in this paper. And before I move to showing the solution, let me just motivate the scenarios under which this correlation can happen. One scenario is where the node deployments can be very dense, so the measurements become correlated. Another scenario is when the measurements by the different nodes are distorted for some reason, and then again there is correlation between the measurements, and even when conditioned on the hypothesis. So here is the first approach that we propose to tackle correlation, and it is called the eigenvalue bound based approach, EVBA in short. So the idea is relatively simple, but it uses a neat trick. So recall that the decision statistic is this quadratic y transpose gy. Now I can use eigenvalue bounds, very classical bounds, to upper bound it and also lower bound it. So the upper bound would be the largest eigenvalue of the matrix G multiplied by the Frobenius norm squared of the measurement vector y. And if you open it up, it consists of two components. One is the measurements that have been received till now from the k-best nodes, and the measurements that are yet to be received from the k-best nodes. And here, in short, I'm referring to y square itself to be the measurement instead of y. Similarly, I can lower bound it by the smallest eigenvalue of G multiplied by, again, the Frobenius norm squared of y. Now, unlike the decision statistic which had cross terms, you can see that these upper and lower bounds both have no cross terms. So in a way, you can now implement them in a distributed way. And the idea is very simple. For example, I know, let's take the upper bound. So if I can take this upper bound and also bound the terms that are yet to come, and I recall I said I can bound them because they're transmitted in an ordered manner, so I can bound this term also. Therefore, I can bound the upper bound even further by some other larger value. If I know that that larger value is less than beta, then I know surely that the fusion node is going to decide H0 eventually. So I can right away make a decision just based on K measurements. Similarly, if this lower bound also, I can bound this unknown term uh, on the left side. So I can bound this, I can lower bound this further. And if this lower bound is greater than this threshold beta, then I know surely at the end it's going to still make the same decision, which is H1. So I can then right away make a decision based on K measurements. And if I can't make either of these two measurements, then I just wait for one more measurement. So that's the basic philosophy. I'm going to skip the math, but essentially present the scheme. So the key idea is that you no longer order the nodes based on LLR, forget it. You order the nodes based on the absolute value of the measurements. And when the node transmits, it transmits its measurement itself to the fusion node. So the fusion node can then compute this quantity, the sum of the received measurements, and then do basically these comparisons. So if you do that, so if you make those comparisons, then you can come up with a set of decision rules. These are what the fusion node follows to arrive at a decision of weight for the next transmission. And so let the fusion node have received the k-best measurements, y1 to y square bracket k, and say the smallest eigenvalue of g is positive. Then what the fusion node should do is take the measurements it has received till now, add them up, multiply it with the smallest eigenvalue of g, and compare it with the threshold alpha. If this is true, then it declares H1. Otherwise, it takes the measurements it has received, multiplies it with the largest eigenvalue of G, and sees if it's below some other lower threshold, alpha minus a quantity that depends on the kth largest measurement or the most recent measurement that it has received. And if this is true, it decides H0. Otherwise, it waits for the next transmission. Now, this constant alpha is basically a system parameter. It is a function of beta and a couple of other things that the fusion node can compute on its own. I'm skipping the details. I request you to read the paper about it, but basically the fusion node knows it. And there are corresponding decision rules if the smallest eigenvalue is negative, but the largest eigenvalue is positive, or the smallest eigenvalue of G is negative and also the largest eigenvalue of G is negative. So there are some minor changes in the signs that have to be handled, but it can be done. Now, the second scheme that we propose is a refinement of EVBA. So let me give you the basic idea behind it. In EVBA, recall that what we did was we bounded the quadratic y transpose gy. But let's take a closer look at the quadratic. So if you open it up, again I'm skipping the steps, you can write it as a sum of two types of terms. The first is this R transpose pk. Now let me tell you what the notation is. R is the set of measurements that have been received till now. So if you've received the k best measurements, this is the vector R. And P is the submatrix of G corresponding to this K received measurements. So essentially, you take the submatrix of G and you compute this quadratic R transpose PK. So the fusion node can compute this. It knows it exactly. We don't need to bound it. But then there are these other terms. For example, U is the set of measurements that are yet to be received. So from the K plus 1th best node to the nth best node. Q is the submatrix of G corresponding to these yet to be received measurements. One important point to note here is that in fact Q is also not computable by the fusion node because it doesn't know the order in which these remaining nodes will transmit. And similarly, this vector V is also something that the fusion node doesn't yet know because it doesn't yet know the order in which the nodes are going to transmit. So basically, instead of bounding whole of y transpose gy, which involves bounding receive measurements also, which is pointless because I can in fact compute this exactly at the fusion node, we only bound the unknowns, these two terms. And that's the idea behind RMUV. I'll skip the mathematics behind it. This is the key idea. I request you to read the. But if you do that, you can come up with a different set of decision rules, again in which the fusion node now looks at the measurements it has received till now. It computes a quadratic R transpose pk and then compares it with a lower threshold, in which case it declares H1, compares it with an upper threshold which it can compute, and you can show that this can be computed. It declares H0 or it waits for the next transmission. So that's the received measurement EVBA, refined version of EVBA. So now let me show the performance of this scheme. So we'll do it for a very general correlation model, and for performance what we'll study is the average number of transmissions. The smaller the better, And we know that the error probability is the lowest possible value, so we don't need to compare that. And we'll do it for a very general model. Under H1, the y is a Gaussian random variable with the mean 0 and a covariance matrix R. And under H0, y is basically just noise only measurement. So the covariance matrix is an identity matrix with a variance sigma naught square. So now for this, to generate this R, you use a general model. This is the product correlation model that was studied by Bolu several years back. So Rij, the ijth element is sigma 1 square, so essentially some sort of a variance scaling multiplied by a quantity called theta I and another quantity called theta j. So essentially you can think of theta I as a contribution to the correlation coefficient from node I. And in our simulations, in fact, we use different theta i's for different nodes. So we uniformly sample the interval 0.25 to 0.75 and use different theta values from that. And so you can see this is a very general correlation model, a very general covariance structure, just for illustration purposes. And signal to noise ratio will define it to be the ratio of this sigma 1 square to sigma naught square. So more the SNR, more separated the hypotheses are. So here I'm plotting the average number of transmissions as a function of the signal to noise ratio. And I'm plotting it for the unordered transmission scheme in which all the nodes transmit. So this doesn't change as a function of the signal to noise ratio. It's equal to the number of nodes, which is 20 in this example. And this is the EVBA scheme, and this is the refined version of the EVBA scheme in red. And you can see that as the signal to noise ratio increases, the average number of transmissions decreases. For example, at an SNR of 10 dB, the average number of transmissions is about 4. That means you need a factor of 5 fewer transmissions than the conventional scheme. So essentially energy efficiency is improved by a factor of 5. That's a huge gain. As the SNR increases, the average number of transmissions in fact decreases to 1, which is the absolute minimum any scheme needs. And in this case, you have a factor of 20 reduction in the average number of transmissions. And another thing to notice is that the refined version requires fewer transmissions than EVBA, just because it is smarter the way it bounds things. Now let's study the effect of correlation. Well, correlation is the heart of this paper. So for this, I'll use a different correlation model, which is the uniform correlation model. So this covariance matrix R for H1 has this following structure. For all off diagonal elements, it is equal to rho multiplied by the scaling constant sigma 1 square. Otherwise, it's equal to 1 multiplied by the scaling constant. And rho is essentially every pair of nodes is uniformly correlated. That's why it's called the uniform correlation model. And again, H0 is the case where you have only noise only measurements. Again, we're plotting the average number of transmissions as a function of now the correlation coefficient. So correlation coefficient of 0 is the nodes are independent, and correlation coefficient of 1 close to 1 means the nodes essentially make the same measurement. And again, we are plotting the performance of UTS, which is always 20, which is the number of sensor nodes, and the performance of EVBA, which is in magenta, and the performance of the refined version, which is in red. We are doing this for two different SNRs, 5 dB and 10 dB. So like we saw last time, as the SNR increases, the number of transmissions decreases. But there are several more interesting things to notice here. First is, let's look at SNR of 5 dB, because things are most clear there. As the correlation coefficient increases from 0, the number of measurements is increasing, because essentially each measurement, number of transmissions is increasing, because every new measurement you get conveys relatively less information than in the independent case. And this is true for EVBA as well as RMEVBA. Interestingly, for very large rho, around 0.7 plus, you can see that in fact the average number of transmissions start decreasing again. Here also you can see it decreases for both EVBA and RMEVBA. And the reason is basically that the hypotheses start getting separated more and more for very large rho. For a detailed explanation, I request you to read the paper. It's very interesting, but you can see that the correlation coefficient has a profound influence on the average number of transmissions. And another thing to note, like before, is compared to UTS, you're still saving a lot in terms of the average number of transmissions, except of course when the correlation is very, very large. So for example, at correlation coefficient of 0.5, you're saving roughly 50% using these ordered transmission schemes at 5 dB, and around probably 80% or 70% using these unordered, using for SNR of 10 dB. So let me conclude. So we looked at the ordered transmission scheme, which essentially gives you better energy efficiency without compromising on performance, which is the error probability. And the key thing was that we looked at a case where the measurements between the nodes are correlated. And this is a generalization of what's been studied. And I should also point out that there are even more generalizations possible. What I looked at in this paper was the case where the measurements are, where the covariance metric is different. You can also consider cases where the mean vector is different, or both the mean vector and the covariance metrics are different under the two hypotheses. And turns out that you can take this approach and generalize it and make it handle those cases also. So thank you. With that, I'll close. If you have questions, you can write to us. These are the emails. And this is also the URL for the group. If you're interested in the other work that is happening, there's also a YouTube channel link on this website. Thank you. Bye.